Hello, my name is Susan Elizabeth Mullally. I am the Deputy Project Scientist for JWST at the Space Telescope Science Institute. I'm here to highlight some of the scientific synergies between Webb and TESS. NASA's next flagship mission, the Webb Space Telescope, well, quite different in size and observing style compared to TESS, has a lot to offer this time series community. So in this talk, I'd like to describe some of the capabilities of the Webb mission and then highlight some of the science observations that are planned for the first year of observations. Hopefully by the end, I'll convince you that this observatory has something to offer this community, and I will leave you with information about how to get started. So before I discuss the science that we tacked by Webb in the first cycle, I will give you a quick overview of what this observatory has to offer. So Webb is quite different than TESS in both style and size. It has a 6.5 meter mirror with 18 hexagonal pieces, and it'll be sent out to L2. Out there, it'll be passively and actively cooled so that it can reach the near and the mid infrareds without a lot of the heat from the observatory getting in the way. It has abundance of spectroscopic and imaging observing modes that make it a very versatile instrument, where 90% of Webb's observing time is decided by an open call for proposals. So we hope you will think about putting in your observing proposals in the next cycle. Well, unlike TESS, Webb is not suited for month-long stares to measure the variability. It is very sensitive in the infrared, and has 4 instruments with dedicated time series modes that make it an ideal machine for following up interesting stars and planets found by TESS. So to talk a little bit more about those instruments, JWST is decked out with 4 instruments with a wide variety of observing capabilities. This colorful image is not a complete set of all the observing modes that are available on JWST, but it does highlight some of the spectroscopic and imaging capabilities of Webb. You can see that it contains the ability to perform multi-object spectroscopy across wide fields with slitless and IFU modes in both the near and in the mid-infrared. It also contains chronographic imaging to allow you to see dim planets or disks orbiting bright stars. What I've done in this figure is highlight in orange some of those modes that support time series observing. In a time series mode on Webb means, among other things, that if the dithering is turned off and the exposures can exceed 10,000 seconds. Plus, there's a dedicated pipeline branch to those time series observations. It essentially means that it treats each integration as a separate exposure. As a result, you can do time series spectroscopy and imaging across the near and mid infrared with JWST. So just this last spring, the entire Cycle 1 program was selected by the TAC. I want to give you a quick overview of some of the science that came out of that call for proposals. In the end, we have the first cycle for JWST has more than 10,000 hours of observing time. So as a result, it will take more than a year to complete. It includes basically 3 calls for proposals, one by the guaranteed time observers. There was also an early release science program that has around 500 hours. All of these observations will go public in the first 5 months after JWST starts observing. And all of those data have no exclusive access period, and they represent a broad range of science. Finally, in the spring, we selected the general observing time. There's about 6,000 hours of observations here that cover a wide range of astrophysics and planetary astronomy. If we take a quick look at what that range looks like, you can see how it's split up between different areas, between galaxies or the large-scale structure. What probably interests this group most is the fraction that is made up by exoplanets and disks, or stellar physics. And I dare say that the reason why, in part, why that exoplanet and disk section is so large is in part because of the wonderful targets that TESS provided for JWST observers to dig deeper in. So before I go into more of those observations, let me remind you that the JWST, that I'm going to be going through a lot of the different programs that JWST is going to provide, is going to observe. I have left off program names because I've combined things together and didn't, and so it would be very spotty even if I did. But all of the abstracts and the observing programs for everything I'm going to talk about can be available from this website if you go under Science Execution and Approved Programs. So you can see the programs for Cycle 1, General Observer, ERS, and GTO, and even the calibration programs. So you should go check that out. So let's first talk about exoplanets. This is a very natural synergy between TESS and JWST. In fact, it was part of the reason why TESS was launched. So essentially the story, or the cycle of exoplanet characterization goes, is that TESS, with its 4 amazing cameras, is observing large patches of the night sky to look for at the nearby brightest stars for evidence of a transiting exoplanet. So when it sees these periodic small dips in the brightness of stars, we can say, aha, there's probably a planet there. And then after some follow-up work where we can confirm the planet and measure its mass, that planet is handed over to JWST TAC, where people say, I want to know more about this planet. I want to look deeper at this planet and start to understand its atmospheres. And JWST allows people the opportunity to think about the planet in terms of the light that's traveling through the atmosphere, also the light that is being emitted as from the atmosphere. And so through transmission spectroscopy, phase curves, and eclipse observations, we can put together a full, rich picture of the physics and chemistry that are going on in the atmospheres of these planets around that are orbiting nearby bright stars. But of course, one isn't going to be enough for us. And we ask, is this planet typical? Can we start to compare planets against each other and really figure out what's influencing why one planet is different than another? And so that's where we need to get more planets from TESS. Of course, the other thing that TESS is providing is that it is holding on to the ephemeриdes of these planets so we know when they transit, which allows us to plan more accurate, more efficient observations with JWST. So to prove to you that TESS has had a strong influence on Cycle 1 science in terms of exoplanets, I can show you this figure of the planet radius versus the equilibrium temperature of transiting exoplanets that will be observed during the first cycle of JWST. I've plotted the general observer programs in orange and the GTO programs in red. And you can see that JWST is going to explore a diversity of exoplanet atmospheres across a range of sizes and temperatures, as well as age and stellar environment, everything from hot Jupiters to lava worlds to cold gas giants because of that one transiting exoplanet around a white dwarf star. But what else you can see on this figure is that I've highlighted with a white box those planets that were discovered by the TESS mission. And you can see that it has completely filled out those planets that are smaller than 4 Earth radii. And so TESS has had a strong influence on the JWST Cycle 1 program and is giving us the opportunity to explore these smaller planets in more detail. And so some of the questions that people are asking in these programs is to try to pull together the first real comprehensive look at the composition and formation of planets that are smaller than 4 Earth radii. They're using NIRSpec and MIRI and NIRISS in their time series modes to use transit spectroscopy, eclipse spectroscopy, and phase curves to study the atmospheres of these planets. For instance, it's unknown whether these terrestrial worlds that are orbiting the M-dwarf stars in particular can actually hold on to their atmospheres. And so Webb will determine which of these planets actually harbor an atmosphere. Those that do, we can start to look at the basic composition of these sub-Neptune planets, looking for things like carbon dioxide and methane. For those really hot lava worlds, have the opportunity to see if they even have an atmosphere. And if they do, as it gets colder, does lava condense out and does it rain lava then on the surface of these planets? Of course, the synergies with TESS and JWST don't end entirely here. Just like TESS, JWST is also going to look for planets, but the planets that it's looking for are very different than those that TESS are going to be finding. Whereas TESS is looking for short planets that transit its star. JWST is searching for new planets that are in much wider orbits, and in general are looking to detect young Saturn and Neptune analogs at very wide separations. For instance, there's a program that's planning to detect giant planets that are sculpting the disks that were imaged by ALMA, shown at the top here. There's also programs to look for planets around white dwarfs at wide separations. In general, it's been proposed that these giant planets are throwing planetesimals in towards the star. So there's a few to look at field stars and some in clusters for evidence of planets around white dwarfs. There's also a program to search for the nearest exoplanet by searching for giant planets around Alpha Centauri A. Of course, the synergies between TESS and between TESS and JWST doesn't end with exoplanets. There's also plenty of stellar physics where I think these two communities overlap. So let me just highlight a few of those. Let me start by mentioning that one way that TESS is pretty much helping out everybody who does Webb observations is TESS will continue to monitor the spectrophotometric standards that JWST is going to use to calibrate the fluxes it produces as it observes. There's a candidate list of A dwarfs, G dwarfs, and white dwarfs, and because TESS has the ability to see if these are varying at all, it can influence then which are the best candidates, which of these stars are the best to use to calibrate JWST. If you want to know more about this, go check out the poster by Michael Kuntz at this conference. In terms of stellar physics, JWST is going to look a lot at brown dwarf stars and free-floating planets. It's using imaging and slitless surveys for brown dwarfs in at least 3 young clusters, including NGC 1333, shown here. It's going to characterize the physics and chemistry of brown dwarf atmospheres, measuring the distribution in clouds on a couple of brown dwarfs using time series spectroscopy. It's going to examine a brown dwarf pulsar with NIRISS in order to confirm the link between the infrared and optical variability they're seeing and that magnetic activity, which is assumed to be auroras, much like we see on Jupiter. It's also going to obtain spectroscopy of another 49 brown dwarfs and look for multiplicity amongst brown dwarfs using a technique called kernel phase interferometry, using images from NIRCam. There are science programs to look at compact objects like white dwarfs, neutron stars, and black holes. One is to use microlensing astrometry of a background star in order to precisely measure the mass of a white dwarf. Very, very few white dwarfs have a couple percent precision masses measured, and so this will be a significant improvement on the number of white dwarfs that we have this sort of this precision for. There's a program to measure a slowly spinning neutron star every quarter second to detect its pulsations. And there's a MIRI low resolution spectroscopy program to look at the jets from black holes. Also of interest in this community is that there's probably overlap between Webb observations of supernova and TESS's observation of supernova explosive events. JWST is going to try to understand the physics of supernova explosions and their contribution to the formation of elements in our universe. It's looking at all stages of evolution of supernova remnants represented in cycle 1, and is even looking at things like the Crab Nebula and supernova 1987A. Webb is going to look at kilonova potentially. It has a target of opportunity observation in there that will be triggered by detections by gravitational waves. And so while there's a lot more I could talk about in this, I wanted to leave a little time to tell you how to get started, because there's going to be many more synergies, and those synergies are going to come from you. So please insert your ideas here. How can Webb advance your science? So just to give you an idea of where we're at, Webb is planning to launch at the end of this year. Right now, it's looking like the end of November or so, even though we'll be ready by the end of October. 6 months after launch, there will be commissioning will end and science will start to flow into the MAST archive. Some of that science will have 0 exclusive access period, so everybody will be able to see it and start to use the Webb data. 5 months after that, the cycle 2 call for proposals will come out, at which point you have 2 months before you to submit your cycle 2 proposals. So I recommend if you're planning to think about what to do with Webb, start now. Start thinking about your cycle 2 proposal ideas now. So just a few ideas of how to get started with that. Get familiar with JDocs. If you haven't already looked, this is where all of your documentation related to the instruments and the observatory are located. In the future, look out for new and improved time series observations section to help you plan those observations. Also keep in mind that once commissioning ends, we'll be quickly updating JDocs with more information about the instruments as it becomes available. Be sure to make use of those early release science programs that have 0 exclusive access period and will be taken in the first few months. So find out what they are and see if they can help you figure out what you want to do in the future with Webb. And you can start now familiarizing yourself with the Webb data. You can attend a virtual webinar called the J Webinars, where we go through in detail some of the workflows related to JWST data. Or you could download some of the high fidelity simulated data that is available right now and try to churn it through your tools or use some of the tools that we have available for you. And of course, if you have any questions at all, please send them to the help desk. They're extremely useful and extremely friendly. So with that, I hope you've been inspired by some of the science that we performed in the first year of Webb's mission, and I look forward to hearing about the future ways JWST and TESS observations can work together to advance our understanding of astrophysics. Thank you.